Okay, so to look at the relationship between black hole mass and equivalent width, we selected a representative sample of AGN from the SDSS DR7 quasar catalog. And since we specifically want to look at the relationship for the broad H beta line, that's the line we're worried about being able to see and like fit cleanly in the spectra. So to ensure that it's clearly visible, each AGN must have a redshift of less than 0.5, and the data can't be so noisy that we can't see the actual line. Then from the sum sample of low redshift quasars, we plotted a full width half maximum of the broad H beta versus the log of luminosity at 5100, and divided the plot into a grid with increments of 0.5 on the x-axis and 4000 on the y-axis. So theoretically, as you move from the bottom left of the plot to the top right, the black hole mass should increase. So we should have a wide range of black hole masses within our sample. And finally, within each box, we selected one quasar with the median I-band absolute magnitude. And ultimately, we ended up with about 20 quasars of varying masses to fit their spectra. So to actually fit the spectra, we modified sample code created by Sarah Roseborough, which mainly uses PySpeckit along with other astronomical and line fitting Python packages. So the first thing we did was plot the original spectra, which you can see in blue on the left, just to see what we're working with, what kind of shape the line profile is, and how high the redshift is. So here's an example from our sample that was fairly simple to fit. On the right, at around 9,000, you can see a large H alpha, and then around 6,600, you can see H beta, and then the two oxygen 3 lines to the right of it. So right in that area is what we want to actually fit. You can see that there is noise in the data, but the H beta and oxygen 3 lines are clearly visible, so it should be a good example to fit. So the first step to actually fitting these lines is to mask out the emission lines and interpolate the data in the gaps that are left in the continuum. So in the plot on the right, you can see the emission lines in blue, and what's left of the continuum is in orange. And then, so here's the fit, of the continuum in purple, with the orange is the interpolated data, and the green line is the polynomial that we use to fit the continuum. And then from here, we use the continuum fit to subtract the baseline. So we end up with a flat spectra, which you can see in green on the right. And then from here, we move on to actually fitting H beta and oxygen 3 with Gaussian components. So here's the final fit that we obtained for this example. You can see 6 Gaussian components in blue. So there are 2 for each oxygen 3 line on the right, and then 1 for H beta narrow, and then 1 for the broad H beta. So, and the red is the combined fit of all of the components. So this was a fairly straightforward example because both of the narrow and broad H beta could be fitted with just 1 Gaussian. And from this fit, we want to measure the center wavelength, the amplitude, and the sigma or the width of the broad H beta Gaussian. We then use these properties to calculate the equivalent width of broad H beta. So equivalent width comes from the total line flux and the continuum density at the continuum flux density at the line center wavelength. So for this example, with just 1 Gaussian component, the values are measured directly from the Gaussian. So the total line flux is just the area under the curve, and the continuum flux density comes from the value of the continuum fit at the line center. And then, so that previous example was fairly simple because broad H beta was only made up of 1 Gaussian component, but in our representative sample of the quasar catalog, it turned out that the majority of our spectra would not be this easy to fit. So many spectra had oddly shaped line profiles that required more than 1 Gaussian component to fit broad H beta. So here are 2 examples. In the bottom one, you can see that H beta is asymmetrical. So 1 Gaussian would not be a good fit, clearly. And in the example on the right, you can see that the H beta line is actually broad enough that it overlaps with the oxygen 3 line. So multiple Gaussians are necessary here because of the way different lines combined together and created an asymmetrical profile. With these cases that needed multiple Gaussian components, there was not a clear way to obtain the same line measurements as we did in the previous example. So the main things that we focused on measuring so far are the line center wavelengths and the total line flux, because those are used for the equivalent width. So the total line flux is just the sum of the flux for each of the individual components. And to calculate the line center wavelength, we took the flux weighted average of the line centers of each component. That way the center is more heavily influenced by the larger part of the total flux. We also have to measure the amplitude and the sigma or full width half maximum of these example of these AGN2, but that is more complicated to define because they're like different, each component has its own amplitude and width, so we have to think about how to actually measure that.
Okay, so while we were doing the fitting and everything, we came across very notable features, such as 1420 on the left here. We noticed that this could be a possible candidate for recoiling. Though it was not in the final selection of the sample, it could have been a binary black hole merge or a gravitational wave or a recoil kick. And then to the right here, we have 1684, the spectra of 1684. And this is a really good candidate for broad wings. It could be a sign of a very fast rotating disk and the outflow of Lute shifted gas, which means that it's coming towards us. And the broad wings are also associated with lines arising from permitted and semi-forbidden lines transitions. We also found that the velocity of this could be around 27,000 kilometers per second, which is about 9% the speed of light, which is really interesting. And as far as future work, this is also work in progress. So ideally, we want to plot equivalent width versus black hole mass and equivalent width versus full width half maximum. Of course, we'd also like to add error bars, and we'd also like to measure the velocity offsets between the broad lines and narrow lines and the broad wings. Since very few profiles could only be filled with one component, we'd also like to add more to the sample and look at them and really spend time on each one. And also, since they are fitted by an automated routine, and we also see a big variety of shapes, it makes us wondering like how well these automated routines are doing. And perhaps it may give us an idea as to why there was no clear relationship in the graph we made that I mentioned earlier. And so without looking at each one in detail, it wouldn't be easy to accurately measure them. So that would be another idea for future work. We'd also like to give a special thanks to Dr. Robinson, Sarah Rasborough, and all of the AGN group for all the help and for all the support. Thank you.